de ma proprio qui est du style in your face. J't'écœuré de ma voisine qui chiale parce que trop de bass. J't'écœuré du monde qui cherche le trouble. J't'écœuré de travailler pour me rendre compte qu'il y a des personnes qui font le double. Qu'il y a des problèmes trop deep pour les résoudre. J't'écœuré de voir combien.
Okay, so when we last left off, we were talking about quantum statistical problems, and the general theme of which was the following. There's some unknown quantum die or mixed quantum state, and has some probabilities, P1 through PD, and associated, unit orthogonal basis vectors, U1 through UD. And you're given n copies of it, and you want to design some kind of measuring device for these n copies, which, if you recall, is just an orthogonal decomposition of your choice of the space in which they all lie together, which is an n-fold copy, tensor product copy of d-dimensional space. And you're trying to use this measuring device to learn something about this quantum state. So once you plug your quantum dice into this measuring device, it gives you back one of these quantum events, h1 through hm. And given what you see on the the readout, you might be able to, let's say, estimate all the p's and all the u's. This is sort of the full quantum state learning problem. But you don't have to necessarily do it all. You might just be interested in estimating the p's, and perhaps you don't care about the u's per se. You might be trying to estimate the entropy of this probability distribution, which is the von Neumann entropy of the state, as it's called. Test the hypothesis that P is the uniform distribution. There are many, many things you could be trying to learn about this quantum state. Now, to talk about how we're going to do that, let me contrast it with the classical case. So, classical statistical problem is, let's say there's an unknown classical die. It's got some probability distribution, P1, PD associated to it, some probabilities for all the faces. And you get n identical copies of this die, and you're allowed to roll each die once in some sense. And you could imagine trying to, build a measuring device that takes in the n rolls of the dice, returns the result of this quote-unquote classical measurement, which is just a partition of all the rolling outcomes into some events, h1 through hm. And again, based on what you see, you could try to, estimate the probabilities of all the faces, or maybe you're just trying to estimate the entropy of the distribution, or maybe you believe that it's a fair die and you're trying to check your hypothesis that P is the uniform distribution. Again, many things you could be trying to do. Okay, so when you phrase it, this way about the classical case, one immediate question that probably is springing to your mind is, why involve this measuring device? Why think about a measurer? I mean, why not just, roll all the dice and look at the outcomes? In other words, have the trivial measurement that gives you the partition into all d to the n possible, singleton outcomes. Well, let me try to explain. The reason, or one reason, is that there are clarifying measuring devices that you can use that don't actually, make your life worse. So let me give an example of that. Let's suppose that you're given n copies of a classical die with probabilities P1 through PD, and you want to do the most obvious task. You just want to estimate all the PJs, full learning, figure out all the face probabilities. Well, there's really no mystery about how you would do this. You roll the n dice and estimate the empirical frequencies. So let's dive into that a little bit more. So as I said before, it would seem there's no reason not to just use the trivial measurer. So plug all the dice into it. The measurer rolls the dice and just says, okay, the first outcome was 3, the second outcome was 1, the third outcome was 2, the fourth outcome was 2, etc. And actually, you can see as you're getting this information, it's actually really a little bit more information than you need. Because honestly, for this purposes of trying to estimate all the face probabilities, you don't really care the order in which these outcomes came up. You really just want to know how many 1s came up, how many 2s, how many 3s, etc., how many 6s. And in other words, you'd rather sort of forget the ordering of the n outcomes. In other words, what you're really, just looking for is just this partial information. What is the histogram of the rolls? How many 1s were there, how many 2s, etc. And therefore, rather than using the trivial measurer, you're just as happy to use what one might call the histogram measurer, which takes all d to the n possible outcomes and groups them together into the ones that generate the same histograms, which are, the ones that are the same up to permutations of the n outcomes. And so this is, a measuring device that you're willing to use, this partition into histograms. Okay. And, once you get back this readout on your measuring device, which is now a histogram, F, with rows, F1 is 5, F2 is 3, for example, then, there's a natural way to finish the job. You would naturally output as your estimate p hat j for the jth phase probability, the frequency of the jth outcome in the histogram divided by n, the total number of rolls. And this is a great algorithm, and it's very natural, and it's not hard to analyze either. I can leave this as an exercise. If you use this simple algorithm, then this notion of error, the L1 error, which is the sum of the absolute values of the d errors you make, p minus p hat in one norm, in expectation, it's at most root d over root n. Okay, and therefore, if you make n modestly bigger than d, a big constant times d, let's say, then in expectation, you make a very small error. And it's natural that you would need, about d rolls of a d-sided die in order to estimate the d phase probabilities pretty well. Okay. Now, actually, before moving on to quantum things, I want to talk about an even easier statistical problem. Instead of, getting a completely unknown die and trying to estimate the probabilities of all its faces, let's imagine you have some, roughly 100-sided die, let's say. And you have a promise that somebody gave you this die, and it's either what I'll call very rigged, meaning it's almost certain to come up one specific face. Which face you don't know, but there's some face that comes up with probability at least 99%. Or you're promised that the die is what I'll call very balanced. Okay, so it might not be like a perfectly fair die where all the face probabilities are 1 over 100, but let's say every face probability is at most 2%. Okay, so no face is more than 2 times as likely as it should be to come up. Okay, so you're given this die. It's either very rigged or it's very balanced, and you're trying to tell which of the two cases it is. One thing to observe here is that, this is going to be important, this task, very rigged versus very balanced, it doesn't depend really on the outcome labels 1 through D. In other words, it's invariant to permuting the names of the faces or permuting the PJs. If you take a very rigged die and relabel the faces, it's still very rigged. And if you take a very balanced die and relabel the faces, it's still very balanced. Okay, so it's now still the case that, we're happy to just get the counts of how many times each face came up. So we could imagine taking our n copies of the die, putting them into the histogram measure, getting this histogram output. And now let's use this further observation that not only do we not care about, the order in which things came, we only care about the histogram, but we don't even really care about the outcome labels 1 through D per se. So in other words, we don't even really need to know all this information, like how many 1s were there, how many 2s were there, how many 3s were there. We would almost rather forget the labeling of the D rows and just, know that okay, some face came out 5 times, some face came out 3 times, some face came out, however many this is, 9 times, and so forth. In other words, we're just as happy to sort of know the set of counts or multi-set of counts without actually caring about which face is associated to which count. So how can we set this up? One way to do that is to try to put them into an unordered set like this, or equivalently, we could put the counts into a canonical order, which would essentially forget the ordering information. For example, we could sort the counts. Okay. So I'm going to call this kind of object a sorted histogram. And so, for this very rigged versus very balanced problem, I hope I've convinced you that you really only care to know the outcome of this sorted histogram measurer. So when you put the dice in here, this tells you that, okay, the most common outcome occurred 9 times. The second most common outcome occurred 5 times. The third 3 times, 2 times, and 1 time. Okay, and I guess if you saw this sorted histogram with these rows, lengths SH1, SH2, and SH3, now what would remain, we really only need to know this information, but what would remain is figuring out a good strategy for looking at these sorted histogram counts and trying to guess, was this the very rigged die or was this a very balanced die? And I guess with this specific example on the screen, it's not super obvious. I mean, I guess I would imagine it's the very balanced die if I had to guess. It's a little weird that, this first most common thing came up so many more times than the other ones. But it definitely doesn't look like the counts you'd see from a very rigged die, which would look like almost, one super long row and only a tiny bit of, boxes in the other rows. Yeah, so this is, kind of where the sort of algorithmic strategy or brain power comes in, like going from these counts, this sort of histogram, to your guess. And it'll be a little bit easier to think of it, honestly, if we imagine that instead of n copies, you just get 2 copies. I start with 2 because, if you just roll a die one time and you see some outcome like 3, it gives you absolutely zero information about whether this is the very rigged die or the very balanced die. So you really can't get anything going until you roll the die at least 2 times. But actually, as we'll see in a moment, if you do roll the die 2 times or you get 2 copies of the dice, you can make a very good distinction between the 2 cases. Okay, so let's think about what happens when you put, 2 classical dice into the sorted histogram measurer. There's only 2 possible sorted histograms. This one, this row of 2, which indicates that, one face showed twice, or in other words, the die showed the same face both times. And this other sorted histogram here, which simply tells you that 2 distinct outcome occurred. Okay, so let's think of the probability of these 2 outcomes. So what is the probability if you roll, this die twice that you'll get the same outcome both times? Well, the probability that you get 2 1s is p1 squared, the probability that you get 2 2s is p2 squared, and so forth. So the probability that you get 2 of the same, or you see this sorted histogram, is the sum of the squares of the pj's. Okay, and therefore the probability of the rest that you get 2 distinct is 1 minus that. Now, for this very rigged versus very balanced problem, I really want to focus in on the scenario where you see this sorted histogram, where the measuring device tells you that you got 2 copies of the same outcome, or 2 of the same outcome. Well, let's see. Suppose you're in the very rigged case, so one of the 2 probabilities, either P1 or P2 or whatever, sorry, not one of the 2 probabilities, but one of the probabilities of the faces, P1 through PD, is at least 0.99. Then, at least one of these sum ends is going to be at least 0.99 squared, and 0.99 squared is roughly about 0.98. It's at least 0.98. So this whole sum is at least, 0.98 in the very rigged case. Okay, so if the die is very rigged, there's at least a 98% chance that your sorted histogram measurer will show you this picture. On the other hand, suppose you're in the very balanced case where all the faces have probability at most 2%. Well, then the sum of pj squared is at most, we can sort of factor out the maximum p. So it's at most p max times the sum of the pj's. The sum of the pj's is 1, so this whole thing is at most p max, which by definition of this case is at most 0.02. So in other words, in the very balanced case, the chance of you seeing this sorted histogram, that indicating 2 of the same outcome, is less than 2%. So this is great. Like seeing this sorted histogram is either super common or super uncommon, depending on which case you're in. So this is really perfect, and it shows that actually with just 2 copies of the die, or the ability to measure 2 copies of the die, you can pretty much easily tell the difference between these 2 cases. What you do is use your sorted histogram measurement, you get back your sorted histogram SH, and if SH is this, single row with 2 boxes, you guess that it's rigged. Otherwise, you guess that it's balanced. And the probability that you guess wrong, that you guess rigged when it's actually balanced, or guess balanced when it's actually rigged, by this analysis is at most 2%. Okay, so that's great. Okay, but this is supposed to be videos about quantum, so let's move on to the analogous quantum problem. So the analogous quantum problem is almost the same. It's just that, remember, your quantum dice now are not labeled by numbers 1 through d, but they're labeled by unit vectors in some unknown orthogonal basis, u1 through ud. However, we're still going to imagine that your quantum die is either very rigged, meaning p max is at least 0.99, or very balanced, which means that p max is at most 0.02. And, I'd just like you to note that this test doesn't depend at all on the basis. I mean, the basis does exist because these are quantum dice, but, what you care about and what you're promised about only has to do with the probabilities. And, this might sound like a contrived problem, but it's actually quite natural in the quantum world. So the case of a very rigged state is called an almost pure state. So we talked in an earlier video about how the fact that you might be most used to quantum states that are just sort of 100% probability on one unit vector. Those are called pure quantum states. And this very rigged case is kind of like an almost pure state, maybe a pure state that's suffered just a little bit of noise. And a nearly balanced state, or one where all the probabilities are very low, this is sometimes called something that's almost the maximally mixed state, which is sort of, pure noise. So this is a natural task you might care about with 2 copies of a quantum system. Okay, so we have to design a measurer for trying to decide very rigged versus very balanced again. And remember that a measurement, if you have 2 copies, a measurement associated for 2 quantum dice is an orthogonal decomposition of the vector space where everything lies, which is CD tensor CD, into some subspaces, H1 through HM. So we have to design valuable, decomposition of CD tensor CD into some subspaces, which will help us, tell the difference between the very rigged case and the very balanced case. Now, if you're a real lover of linear algebra, you may already have your very favorite decomposition of the tensor product of two d-dimensional spaces into two subspaces. And if you even just know about, basic properties of matrices, you may know about this. So the natural decomposition is into what's called the symmetric subspace and the alternating subspace. So the symmetric subspace is just the span of all the vectors in CD tensor CD that are symmetric with respect to permuting the two tensor components. So span of things that look like V tensor W plus W tensor V. And the orthogonal complement to that, the so-called alternating subspace, is the span of all those vectors in CD tensor CD that look like V tensor W minus W tensor V. Again, this is maybe a little bit fancy, but actually this is exactly the same as the fact that every D by D matrix can be written as a symmetric matrix plus a skew symmetric matrix. Okay, so that's really all that's going on here. And this turns out to be a really great, and natural measuring device or measurement, because it forgets the things we want to forget. It forgets the n equals 2 ordering information, because these two subspaces don't really, they don't particularly favor the first or second tensor component. And that's natural because we just have two n equals 2 copies of this quantum state. There's nothing special about the first versus the second. And similarly, this decomposition into the symmetric and alternating subspaces sort of forgets about the d-dimensional orientations as well. For the problem, we don't really care about the vectors u1 through ud, and so we also don't really care about any particular orientation of d-dimensional space. And you see the symmetric and alternating subspaces also don't have any particular favored direction in d-dimensional space. Okay, so since this is a decomposition into orthogonal subspaces, we can, in principle, build a physical measuring device that takes in these two d-dimensional quantum dice and, measures them and outputs on its screen just one of two outcomes, either sim or alt, according to their projection into those subspaces. So let's take a closer look at that. So, when you take your two quantum dice and you put them into this sim/alt measure, it either shows sim or alt. And let's figure out what is the probability that it shows, let's say sim, that you read out sim. Well, for this, we have to remember the mathematical rules for how quantum measurements work. So I'll remind you of those. They're right here. You can imagine that, nature on the inside of this machine, what nature does is it, rolls the two dice. And so it obtains some outcome, which is really a pair or a tensor product of two of these u's. And, it gets uj tensor uk with probability pj times pk. And then having gotten that, it displays sim on the readout screen with probability equal to the squared length of the projection of this outcome, uj tensor uk, onto the symmetric subspace. Okay, so let's calculate that. Okay, so remember we saw, first of all, when we were studying the classical case, this here is the probability that the two sort of rolls are the same. So with probability delta equal to the sum of the squares of the pj's, the roll will be of the form uj tensor uj for some j. And this vector, uj tensor uj, is symmetric. It's in the symmetric subspace already, so its squared projection length is 1, and we display sim with probability 1 in that case. Now, what about the remaining case? With the remaining probability, 1 minus delta, the outcome will be uj tensor uk, where j and k are different. And here's a little simple thing you can observe. If you have uj tensor uk with j and k different, that's the average of this vector, which is in the symmetric subspace, uj tensor uk plus uj tensor uk, and uj tensor uk minus uj tensor uk, and this one's in the alternating subspace. So when j and k are distinct, this tensor is like basically 50-50 in the symmetric subspace and the alternating subspace. And therefore, in this case, when j or k are distinct, the chance you'll see sim is a half. So putting this together, the overall chance that your measuring device will show sim is delta times 1 plus 1 minus delta times a half, which rearranges to a half times 1 plus delta. So this is what we'll remember. And then, of course, the probability it shows alt is just 1 minus this, which is a half times 1 minus delta. Okay, now let's consider our two cases, either very rigged or very balanced. We saw in the very rigged case where there's some uj with probability that's at least 99%, then delta is at least 0.98. And plugging that into this formula shows that sim will show in the readout with probability at least a half times 1.98, which is 99%. And on the other hand, if you've got the very balanced quantum state where P max is at most 0.02, and therefore, as we saw, delta is at most 0.02, you plug that into this formula, you get a half times 1 plus 0.02, which is 51%. So this is a little bit different, but still good. So to summarize, if you have n copies of a d-dimensional quantum state, and you're told that it's either a very rigged state or a very balanced state, and your goal in life is to tell the difference, if you can get 2 copies and you put these 2 copies into this measurement that's based on the decomposition into the symmetric and alternating subspaces, then in the very rigged case, it'll show sim with probability at least 99%. And in the very balanced case, it'll show sim, okay, with probability as high as 51%, but no higher. And this is still pretty good. You can still kind of tell the difference. Not so great with just 2 copies, but let's say you had, 20 copies. Then what you could do is, take your 20 copies, parcel them together into 10 groups of 2. Take each group of 2, put it into the measurer, see if you get sim or not, and do that 10 times. And in the very rigged case, probably 10 out of 10 times it'll show sim, maybe 9 out of 10 times. And in the very balanced case, it'll probably show sim at most 5 or 6 times. So if you take some cutoff like 8, that's quite reasonable. And I did a little calculation on the side, and it turns out with this cutoff of 8 and this 10 trials of this sin versus alt thing, you again have the property that you'll make the wrong guess about very rigged or very balanced with small probability, at most 2%. So that's neat. And actually, let me tell you some rather practical quantum computing information relating to this. So one thing I can tell you related to practical quantum computing is that it's much, much harder to build a 2 quantum die measuring device than it is to build a 1 quantum die measuring device. Just because these quantum measurement devices, when you actually build them, they have to make the dice or the particles interact. And, if it's just 1 particle, it's not so bad, but to make 2 particles interact in a careful way is tricky. So you might ask yourself, well, okay, we saw we could solve the rigged versus balanced problem pretty well with 2 die measurements. What if you have only a 1 die measurement? And in this case, you might imagine the answer is no. And indeed, this seems very believable because it's very similar to the classical case. And as we mentioned with the classical case, if you're trying to tell the difference between a balanced die and a rigged die, you're pretty much screwed if you only can roll the die 1 time. You can't get any information. So you might imagine a similar thing is true in the quantum case. This turns out to be not so easy to prove, but recently in this great sequence of works by Bubak, Chen, and Lee, then Chen, Kotler, Robert Huang, and Lee, and then Chen, Bryce Huang, Lee, and Liu, they showed that indeed if you have only the ability to measure 1 quantum die at a time, you need many, many copies of it. So, you can have the ability to, have a 1 die measuring device and get many copies and use your 1 die device many, many times. But if you're going to do that, you're going to need a number of copies that scales with d, even like d to the power of 1.5. Whereas we saw if you're allowed to build a measuring device that can just measure 2 particles at a time, you can do a great job with like 20 copies of the device, of the state, independent of d. So this was some really cool theoretical work, and it actually tied into some really cool practical work, really right at the edge of, cutting edge of quantum computing. So in this very recent work by Huang and many others, they literally tried this out like on a cutting edge quantum computing chip. This is Google's Sycamore quantum computer. They tried basically this experiment with D being, ranging from 256 up to about 1 million, because it was involving between 8 and 20 qubits. This was your 1 quantum die. And they really, tested out like how well you can do at this kind of task if you can build a 2 at a time measurer, which they were just barely able to do with this quantum computer, versus a 1 at a time measurer. And, I won't really get into what these numbers mean, but you can see from the pretty picture here that indeed with the 2 at a time measurer, you could solve this task quite well, and with the 1 at a time measure, you couldn't. Okay, so in the upcoming videos, we're going to get into even more sophisticated kind of quantum stats algorithms building on this one.